be talking about entity linking at scale over heterogeneous datasets.
Using Elastic.
Using Elastic.
Thanks. So my name is Atif Khan. I think some of you have probably seen me around for different talks. This is in continuation of the thing that I talked, I think the data science group that I talked about, where we talked about how to present information using graphs and how to link information together using graphs, right? Today what I'll talk to you about is exactly how once you define your entities, how to figure out how to overlay different types of entities together here, how to overlay different types of entities together, and then do that at scale and solve some of the complex problems that Elasticsearch may not necessarily look like the initial first choice. However, for me, it worked out really, really well. And I've been abusing it ever since. So in our case, the problem was as follows. We had two different data sets. They came from two different domains, right? So I'll give you an example. This Twitter data set, and then on the other side, you'll see maybe customer data set or transactional data set. And then the idea was that if I receive these tweets and this tweet tells me something about my product, can I link it back to the person that actually purchased this product and identify which product was purchased? So this is where I started. Now, there's no foreign keys. There's no explicit relationships that are defined between the two data sets, so it's quite daunting the amount of computation that you need to do. If you just play this a little bit, I can maybe extract certain pieces, and this is just a quick wrap of things that I've talked about before. You can apply natural language processing to figure out different pieces. You can use some of the semi-structured information that's available in the Twitter data set, and you can maybe start to make some sense out of it. So if I just look at the last name, and then go back to my customer data set, it's like, okay, I'm just going to go back and just look at all the Smiths, and maybe all these lines I highlight, right, or light up. And then I can say, okay, you know what? Maybe I'm just going to look at Jane Smith, and I'm taking one attribute at a time, and I'm trying to overlay them all together. I'm sure most of us have done this. I'm taking this a step further. You can pretty fast bring it down to a manageable data set. Even though if you look at the worsening time complexity, you're looking at quadratic complexity, however, still manageable. The problem becomes is that it's not just one table that I'm after, right? This graph that I'm looking at, it's a combination of things. So there's product mentions, there's entities, there's relationships, entity attributes themselves. There's a lot of information that I need to start to overlay, right? And the more I can get to this information, the better I can actually pinpoint to the exact product, exact line, and an exact person. So that's the problem we're trying to fix. There are some challenges to this particular problem. If I look at real-world data sets, so this is just looking at, I think, Wikipedia, Twitter, Instagram, and a show website. Same person, different profiles, right? I'm getting different types of information about the same entity, so each platform is capturing something different about this particular person. Nonetheless, if I were to graph this together, it's a big heterogeneous graph of the same person, same entity, just talking about different aspects of it. It's distributed, so I have to go to different platforms to actually get this information. Each platform reports things a little bit differently. So there's schema differences with it. The other challenge is that in the real world, the name Michael Jordan may be good enough for 1 or 2 or 3 people. It may not be good enough to represent everybody who's a Michael Jordan. Right? So this happens all the time. If you go and search for Harry Potter, you know which Harry Potter you're going to get. There's a whole bunch of other Harry Potters that you never get to. The idea is that, well, even if between the 3 that they're most famous for, how do I differentiate between those 3? Without just from the far perspective. Even if I were just look at single Michael Jordan and single data sets, so I'm just looking at Twitter accounts right now. There are 4 different Twitter accounts that talk about Michael Jordan. Okay, so not all of them are Michael Jordans. Maybe one of them is the real Michael Jordan. And if you know a little bit about him, 23 has some sort of, I guess, significance to that was his number. So maybe you look at the data a little bit closer and say, okay, maybe the first one is the real account, right? Well, it turns out that none of them is the real account. It turns out that Michael Jordan actually never owned a Twitter account, right? And it was recently that the Charlotte Hornets gave him free access to tweet whatever you wanted on their website or to their Twitter handle for 1 day. That was the true Michael Jordan, right? And the best part is I don't even know if that's true or not because I'm just believing some other website that reported on this. But you get the picture. Even though if I can get the entities together, if I can put them together, if the data looks realistic, it may not be the right thing. It may not be the correct thing. Okay, so here's maybe not formally, but maybe what the problem looks like. I have two different entities. They have different attributes. They have different number of attributes, and not every attribute is comparable against every other attribute. Right? My problem is that I'm going to try to figure out some sort of function so that I can say that there's a link between the two entities somehow. And in this particular case, I'm going to say, okay, maybe I'm going to limit the output of that function from 0 to 1, 0 being that there's no link, 1 being that's the strongest link, and then everything in between gives me some sort of, let's say, idea of how strong this link is. And as an example, I want to be tolerant to the entities with nodes in them, so the second entity over here doesn't contain the location information, and this is in response to that when you look at real-world data sets across different systems, you're not going to get all the attributes that you need to compare them. In addition to that, in addition to noise and stuff, there's always schema differences. So maybe Twitter records name as one field, and maybe my database records names as two different fields. There's a correlation between the Twitter handle. Sometimes there's a correlation between the name and the Twitter handle itself. How do I say, well, the Twitter handle also gives you some information about it? And then most importantly, when I'm comparing these entities together, how do I know which attributes to compare against which attributes? I can brute force my way through all the different comparisons, but again, that's not computationally feasible. The problem seems grim. Here's some insights that will help us how to solve this problem. Right? It's not as dark. So let's go back and let's focus on two Jordan systems. Right? And let's say we have a whole bunch of other entities, and we're trying to figure out how to make sense out of these entities and maybe what goes with what. Right? So just knowing that there's a whole bunch of entities and two micro-Jordans, maybe not as insightful. However, if I were to use some sort of clustering algorithm that's predicated by maybe a attribute, so in this case a topic, so basketball and AI, right? And if I look at the entities from that lens or from that filter, I can pretty quickly come to this type of distribution or this type of cluster, right? Much cleaner. So having the injection of the two topics, basketball and AI, gave me additional information about how to deal with this information. There's a lot of this little tidbit floating around all over the place. When you look at Twitter accounts, there's a lot of metadata information. When you look at Facebook accounts, there's a lot of metadata information that you can get into and start using that metadata for these type of things. Okay. There are two types of attributes. Or maybe there are more, but in my case, there are two types of attributes. I call them partitioning attributes. And these help me group things together. They not necessarily help me identify things, but they help me group things together. And then the idea behind partitioning attributes is if I were to do a projection on my data along one of these attributes, I can cut down or cut away a large subset of my data. Right? So if I take gender, for example, so just matching somebody by gender is not the best possible match. However, if I were to say, okay, I'm just matching males against males, that's a good start, right? Postal code, profession, those are all different type of things that by themselves, if you match them, they don't really tell you that you have a good match. However, they very quickly allow you to narrow down what's it. The second type of attributes are identifying attributes. So if I were to take one of these and match on those, I have a link between two attributes. The problem is these are costly to compute. Those ones don't give me a lot of precision. They just give me a better recall. So my idea is to combine the two together, right? So we bucket, and bucketing is a very common concept when you do like bipartite graph computations. Bucketing to increase performance is actually a very common concept. Okay, so here's our basic approach that we tried and worked out really, really well. So let's assume that there's only 4 Michael Jordans in the world. Okay? And your task is to figure out which one of them is a duplicate, and you're given maybe 4 attributes, 4 attributes. Name, the age, location, and perhaps the height. No, not perhaps, definitely the height. Missing one. Okay. So a naive approach, shouldn't say naive, but this is how we all start, would be to just do a bipartite graph and then do entity-to-entity computation, right? So I start from this guy, and I say, well, do you match with that? Do you match with this? Do you match with this? And do you match with this? So I compute my function overall. Okay. This computation, each one of these f's that I'm computing right here, happens across all the attributes that I talked about. So across all the a's that I talked about. And we'll see in a second how that helps. And then obviously I can just do the entire graph, right? And I can figure out, okay, so what matches with what. Easy to do on small data sets, much more difficult to do on large data sets. I can use heuristics, so I can use an identity heuristic. So if I match E1 against E1, maybe I shouldn't match against E1 to E1. I understand that they are the same thing. However, if E1 doesn't come, this E1 and that E1 comes from different data sets or different data sources, then I can't use identity because I don't have identity. This is how we started. This is how we got here in the first split. We don't have foreign keys. Or I can do blocking again, and I can figure out maybe I should only match this guy and this guy because they were together in the same height, or they were same cluster of height, or maybe same cluster of location or whatever. I can do blocking of those as well. So those things help. However, they don't take away or they don't help you get the answer in a let's say a feasible way. There's still complexity involved that you need to deal with. Okay. So we're trying to figure out a solution that has these two desirable properties, right? So we can scale to large data sets, and when I talk about large, I would like to be able to do Twitter to Facebook. That's what we did. And I would like to also to do things like Twitter to Metro. Right? So in one case, I'm talking about millions to billions, or millions into billions, and the other ones are millions into billions, right? So it's still pretty large. And then not only that, I would like to be able to generalize it to just all types of entities. So if I want to compare person to person, I should be able to do that. If I want to compare person to item, I should be able to do this one. An entity is an entity. If somebody's bought a book and that relationship can somehow be captured, I should be able to link those two things together. Okay. So why entity linking? Why search? There's known algorithms that we can employ already. There's other solutions that we can use already that help us do entity linking. Right? When you think about entity linking, search is not your first I guess weapon of choice, right? When you look at search, it works without relational integrity. And this is what I mean. When you look at documents across the web for a certain topic, that web page doesn't tell you I'm about this document. All it tells you that I'm talking about, these are the words that I'm using, and then search allows you to go find those things and say, okay, so in my case, I'm interested in you, and you, right? So search by its very nature works on the assumption that there's no big index that exists somewhere, a pointing index, or foreign key index, or relational integrity index that exists somewhere. That's going to tell me that you should go look at document 1 and document 2 and document 3. Right? I can search for those things. By its very nature, it's built that way. If I can somehow take entity-to-entity associations and I represent them using similarity, so are you this Michael Jordan? How similar are you to this other Michael Jordan? Right? Then I can link the two together based on my output of the similarity. Well, I can use search to figure out where the similar items are. That's what we do all the time. We find similar web pages based on our query all the time. So that's how we got thinking, or we got started, and then it down a deep rabbit hole. So I'm going to maybe jump a little bit faster here, but take you to the problem itself. Entity linking is synonymous to document search. Hopefully, I think I haven't stretched your imagination too much here, and I've kind of convinced you that you can potentially do this using document search. This is how it works out. You take an entity, you present it as an Elasticsearch document, or Lucene document. It doesn't have to be Elasticsearch. Elasticsearch is nice for other things. But nonetheless, it's just a document in the search terminology. Right? You take the attributes, and you present them as the document fields themselves. Okay, we should all be familiar with this concept because we're in Elasticsearch unit. And then the idea is that the similarity function that we needed to compute against that entity and across all the other entities is just some search or math strategy that would give me a hit list. That's what I'm really after. So I've taken my problem of doing a bipartite computation, and I said, okay, I'm not going to do a bipartite computation. I'm going to use search instead. Give me automatic bucketing, and I'm going to go and then just basically treat it as a search problem, look at the answer as a search problem, and then see whether I can make sense out of those answers. So this is very quickly the quick summary of the same thing. Entity into a text document. Entity attributes get mapped to the fields on the Elastic slide. Right? You take your relational databases, which may be hierarchical in nature, may have all kinds of foreign keys and all kinds of tables, and you flatten them into a single index. Now, some of you are going to say, well, why are you flattening relational tables into a flat index? It's just easier to work that way. If you can represent entity-to-entity relationship in Elasticsearch, don't go down that road. It's much more painful. Okay? Once you've done that, once you've indexed all your entities, then you can, using one of the entities as the query, you can query it against the index that you have, and you'll end up with a hit list that we were looking at. Okay? And in this case, the nice thing is the hit list is ranked by similarity score. Right? And we can control that, so it doesn't have to be one. I can normalize a score, I can do post-processing a score, but the good thing is the things that I'm most interested in are towards the top half of that list. So Elasticsearch, going back to why we decided to use it, so we actually started for Lucene. Because I was just playing around with this concept. Lucene was easy, it was available, and then once we realized that Lucene doesn't scale, I ended up going to Elasticsearch. But it brings all the goodness with Lucene on top, right? So this is the goodness that I can write my own analyzers if I have to. So we're all familiar with the analyzers, yeah. I can write my own custom scorers, and I can even define my own similarity frameworks. Don't do the last one. Not a pleasant thing to do. However, it is possible. To a point where it gives me flexibility down to a field level. I can take a field and I can manipulate it, I can twist it, I can torture it, I can will it to bend it to my will. Right? It's really, really flexible. There's a query that allows me to do even customizations at runtime. Even better than SQL. And then there's a whole bunch of queries that are pre-written for me. These are complex queries that come out of the box from Elasticsearch. Now I'll talk about some of them today, right? But it's all there. Like I didn't have to build any of this. I put it down there. On paper, it's easy to do. And I think from the previous talk, as you heard, there are challenges. So I'm not going to claim that this automatically scales and then everything is good. You need to understand what you're doing. It's a deep enough topic. I'm just going to leave it at that. However, it is possible to horizontally scale this really, really easy. Much easier than other systems. Okay, so we'll first thing I think that this is maybe echoing from the first talk as well, denormalize your schema. Right? If you have hierarchical relationships, if you have associations that exist in your data, so these are parent-child associations or entity-to-entity associations. We all good with that, right? Term frequency, inverse document frequency tells us the importance of a single word in an index. So if I'm looking for the word to, I understand that it's not very useful. If I'm looking for the word with, I understand it's not very useful. But if I'm looking for some other word, but just maybe, I don't know, Michael Jordan, maybe that's more useful. But in the case where if you have a field and you were trying to compute similarity between the field, you can do that at similarity between the two names by looking at maybe a standardized type of this. So this name sounds like this, and this name maybe morphs to the other name with this score or whatever. And I can actually define a whole bunch of these, right? All I really have to do is I have to define the name field node maybe multiple times, but I can do all these computations on the name field itself. So I have a whole bunch of functions, for example, that describe how to compute distances or similarities or scores for different names. What I can then do is I can use a query like multi-match or diskmax to say, well, my strategy is that I'm going to maybe find, out of all those scores, maybe the maximum score. Or maybe my strategy is that I'm going to find, out of the edit distance and the sound X distance, maybe I'll take the average score, right? So I can actually define, I can replace this H right here with a whole bunch of other averaging functions and roll functions and come up with a strategy like how I'm going to just deal with names. Right? And this is really flexible. It can help you with misspellings. It can help you, like I think this word, the names that there's 56 variations of the same word that exists, or same name that exists. Right? And these are just first names. I'm not even at last name at this point. Nonetheless, you can do this. Right? Extremely powerful. If you haven't ran into this max query, I think multi-match query evolved from this max query. This max query allows you to put all these different types of subqueries and then figure out what strategy you want to use on them. And there's links in there as well to follow on them. But we started from this max query and ended up with multi-match query. Right. So now that you have figured out, okay, so I have first name and last name and location and email, maybe you can define certain strategies, how to combine those attributes together, or how to combine the similarities of those attributes together. A naive approach would be that I'm just going to treat first name comparisons or scores that come out of first name comparisons same as scores that come out of last name comparisons, and maybe I'll just do a weighted average or something. Right? A strategy, different strategy could look like this. That I should always match the combination of last name and location, and then I'm okay if maybe first name matches or email matches. And the way I've written this is I think it should remind you of another query, which is the Boolean query itself that we'll see in a second. But this could be easily mimicked by a Boolean query in Elasticsearch. Okay. I can take different combinations of these things, and I can potentially rewrite them as a compound Boolean statement. Okay. And I can transform that Boolean statement. So in this case, this is one strategy that I use maybe on first names. This is the second strategy that I use maybe in the last names and then locations or whatever, and I can define some sort of and or combination over these things. All of this, if you have felt the pain of writing Boolean queries, as I have, can be expressed really, really nicely using Boolean queries. Unfortunately, the queries themselves get to be a little bit more verbose than you want them to be. The bright side, you can piecewise them. You can break them, you can take this piece, write a query for that, you can break this piece and write a query for that independently, and then combine them together. If you're trying to do it by hand, don't do it by hand. Write templates and write code and do it that way. Much easier to figure out what's going on. Okay, so putting it all together, this is the set of all the entities we started from. We're trying to compute this particular function, which is a match strategy, and it's going to give us our hit list that we talked about. Okay. So in my case, a strategy that we talked about looks like this as a Boolean query. So I'm looking at, I must match on the last name, I must match on location, and then I'm okay with maybe some of these attributes. And then there's enough flexibility in the query structure itself. If you go back and look at the documentation of it, you can actually do really, really neat things with it. You don't have to just do very, very basic things. There's a lot of flexibility that's out there. Yeah, so let's go back to the last part, which is the hit list. So I glossed over before, and I said it just gives you a hit list, and the nice thing is that it gives you scores for the hit list, and that's really good. Well, it's not really good. What it does is it gives you scores, something like this. So I think that first scores before the previous slide gave you a nice 1 and a 0.8 and whatever. You're getting scores that look something like this. So first one is the top rank, second one is the second rank, and so on and so forth. How do you know that the second one is not the actual entity? Right? Maybe you got scored a little bit less because you didn't have all the attributes recorded. Right? So just because something got ranked higher doesn't mean that that's the right answer. Right? So we need to go back and maybe look at something. And if you look at between these two, they're almost similar. The only difference being the location. So one record doesn't have the location information, and that's why you're getting the low score. Okay. So again, this is the same. If you have a hit list that looks like the top one, so you have 1 and 0.9 and 0.8 and 0.8. When you compare entity E1 to E1, E1 to E2, E1 to E3, and E1 to E4, right? How do you know which is the right one? All the scores are very, very close to each other. All the scores are maybe just tell me that they're all good matches. Should I take the top one? Should I take the next one? Like, however, if you were given a hit list that looks something like the bottom H, the decision is actually pretty obvious. Right? So the decision is obvious because there's a separation between the scores. There's a nice separation that exists between the scores. So there's this notion in Elasticsearch or Lucene that you can actually apply weights, or I think the term in the Elastic or Lucene term is boosting. You can apply boosts to your different level. At different levels, you can apply boosts to your search parameters. You can apply boost values to, if this part of my query matches, I want it to be this, have this much weight, and this part of my query matches, I would like to have this much weight. Right? If you boil it down, it looks something like this, where you're maybe doing a weighted average of your weights times the math strategy that you have. And the good thing is, you can now optimize for this. Right? So this should remind you of a regression or a logistic regression type of equation. You can optimize for this, and you can actually learn the weights automatically using machine learning. So this is exactly what we ended up doing, where the idea was if we have a distribution that looks something like this, where a lot of weight is in the center, before, was this notion of penalizing things that didn't match. So if I didn't match, if you recall correctly the Boolean expression that I wrote, I was insisting that last name must match. Right? If the last name doesn't match, there's nothing that I did with score that brought it down. Right? So if now apparently there is a query or mechanism in Elasticsearch that you can utilize to do exactly that. So the negative weighting gives you that this notion that I was telling you gives you the distance between the scores that you're reporting. So then, if you look at the top 10, and then top 3 are the highest scores, and everything else is way below a threshold or whatever, it's much easier to figure out what you're looking at. At the beginning, I talked about entities are made up of different attributes, A1, A2, A3, and then the idea was I need to compare different attributes against different other attributes. Right? So I showed you this graph. There's names, there's locations, there's product information. The notion here is that you should be matching things that are semantically similar, right? Things that have the same meaning. So first name or name has the same meaning as last name, maybe, and then also same meaning as a name in different sets. So name over here, Gene Smith, could be matched against first name or last name over there, because semantically they represent the same concept, same type of information, right? Location, Waterloo, and then the address over there can be matched together. If you can build an ontology, if you can build a taxonomy that can help you understand which attributes are similar, and this can be done independent of the data you have, just by looking at the data sets that you're going to be working with, right? Upfront. It helps a lot in cutting down what computations you need to do. Okay, so in this case, for example, first name I can, from one data set, from Twitter data set, I can match against the user ID. The last name, sorry, this one's reversed. The first name from my customer data set I can match it against user ID. Or maybe I made a mistake there. But last name can be matched against last name from this field to that field from two different data sets. Text could be matched against name, description, and store. So just to give you an idea, there's some text over here. This could be matched against information that exists maybe under description fields themselves to figure out if there's any similarities and so on. Right? That's what you're trying to do. Last piece, so we started with the conversation where I have two different data sets. Most of my talk, I think I fudged you through this talk about saying you have 4 entities and 4 microjordans. I didn't really talk about 2 different data sets altogether, or 2 different distributions of data. So here's my customer index, here's my Twitter index. The first thing you do is you can index them separately. So all my customer data coming in from a database goes to one index, all my Twitter index goes to another, Twitter data goes to the Twitter index itself. Right? I now understand this notion of semantically similar attributes. So first name over here can be matched to user.name over there, last name over here can also be matched to user.name or and so on and so forth. And then what I can do is when I need to match entities from my customer data set to my Twitter data set, I can run a match query or match strategy where I take a customer and I search against the Twitter index itself, Twitter entities. And then if I want to do the reverse way, I can take a Twitter guy and search it against the customer index itself. All it is, I'm just running queries queries from one index against the other index. The bipartite graph that I showed you initially. Just a different version of it. The trick being is, how do you take this customer and then map it to the query that the Twitter index can answer, right? And that's what the concept of semantically similar attributes is. Okay, so here's a quick summary of what I talked about today, right? Index your entities. I will say index each type of data set that you have separately, gives you a lot of flexibility. You can mimic the linking part using a search algorithm. You can define extremely powerful queries using Elasticsearch. And then whatever answer that you're getting in the end, you can definitely, you don't have to use the default scoring, so you can optimize the scoring strategy all the way from writing your own custom scores to optimizing the scores themselves and weight themselves for the queries that you're doing. Yeah, thank you very much. Any questions?
So that map of field names from one index to another, do you build it manually or did you figure out how to?
So initially we built it manually because the data sets themselves, there's not a lot of data sets, right? And I said we can build it upfront without the actual data. We just need, like, I'm looking at Twitter, I'm looking at Facebook, I'm looking at custom data. So initially you can build it manually. You can also look at papers and work that talks about automatic data mapping that exists between relational database schemas.
That's what I was wondering about.
Yeah, so you can do some of that tooling as well. However, it's error prone. Right? It works to a point and it breaks. But you can definitely apply the same type of notion, same type of concepts here. The good thing is if you build an ontology or reuse an ontology, it doesn't go away. You just keep adding to it. So it's work that you've done once and you're getting gains out of it multiple times. Right? Yeah?
You said about Facebook with Twitter, if profiles are closed for friends, how you can get this information to your database?
So we get our clients to get that information. The notion here was not to collect the information, right? So I started with the assumption that the information was there. Now in some cases, for example, maybe the Twitter stream that I'm looking at, maybe it's one-sided because one guy's blocked or one guy's private or whatever, right? The example is if you ever, like, back when you were little and your mom was talking to your aunt and they were making plans for Sunday meal, you were still listening to one side of the conversation, but you knew what they were talking about. There was enough keywords that were mentioned in that conversation that you can say, oh, they're prepping up the Sunday meal or Sunday dinner or whatever, right? You can do the exact same thing here. If they're both blocked, that there's nothing to do about it. But the notion here is not to capture data in real time. The notion here is once you have captured the data, how to create the links together.
How does it scale when you're matching millions to billions versus million to millions?
So I think we didn't do billions. Billions is the actual number of, we did millions to millions. Our worst case, I think we're looking at 700 million to 500 million, something like that, ran for 23 days. And I think the cluster was about like 16 nodes or 17 nodes. I don't remember. It ran for a while. And then some of it was just naivety on our part, right? It's just, things are not tuned properly. Maybe the queries were written in a way that they're spending more time querying stuff. But that became our hallmark. Everybody joked about it. It was like, good, never a game. But it can actually run for a few days. Now, the good thing is we could have built a bigger index, or we could have built maybe a better query mechanism. The Boolean query is really the key here. And then if you take your Boolean query and map it back to a Boolean algebra, you can reduce it really, really well. Right? So you can take a really, really long Boolean, compound Boolean expression, and instead of using 20 different operators, you can maybe reduce it down to 3 different operators by doing reduction of the Boolean algebra itself, right? So if you can map your Boolean query back to Boolean algebra or compound statement, you can definitely optimize that query that way.
Yeah, the use case I have in mind is for Ontario.
Yeah.
Set of population, 10 million, 15 million.
Yeah.
And so when you go to various hospitals, various locations, you're registered with slightly different names or typing errors and stuff. And when at a central registry, you have to identify that this is the same person who went to
different places, right? Yeah.
So you have to kind of do all of this, plus some more,
Yeah.
to give weightage and, identify which are the key aspects versus the optional.
So the very first two slides that I went through were where I was intersecting different attributes and was reducing my potential hit list or potential candidate list. That will help you greatly there, right? Even if you know that the disease is the same. Maybe that person is seeking drugs or whatever, right? Or maybe he's just asking for the same drug at every single hospital. Or maybe he's coming with the same symptoms every single hospital because he's not satisfied with one session that he had at one hospital, right? Even if you know certain other attributes, they help you reduce the candidate list. They help you narrow it down very, very fast, right? The cool thing is parsing out the additional metadata information around it, right? If you don't do that, then this won't magically solve everything, right?
Yeah.
But
We did this with RDBMS,
yeah,
and it works really well, but there are certain edge cases where that doesn't work.
yeah,
And for example, one person, actually one name, one date of birth, and same address.
yeah,
You would think it's the same person. But there was one case in the history
Yeah.
that it was actually two people,
yeah.
but both lived at the same
Same place, same name.
same name, and same date.
So the problem with relational databases, so you're right, you can definitely do it with relational databases as well. You can't do any inference. If you haven't explicitly defined a relationship, in my case I was working with graphs, because all this came from graph, and then we want to see how two graphs come together. You can infer over graph information by just traversing through it, right? If you need to do this at scale, the joining that you need to get to that point breaks relational databases, especially at that scale. If you don't flatten, it's game over, right? So we stayed away from relational databases just purely from that perspective. However, if you can get that, let's say, hierarchy controlled in a way that you can express that, by all means you can use relational databases as well. The part that you have to work on is writing all the parsers and processors at field level, comparators that you're getting out of the box for free.
Yeah, we did that. And
You did
we did the weightage as well in
Yeah.
the relational
Yeah.
system. It took like 6 months.
Yeah. It's incredible how logistic regression came back. I was so happy.
How you deal with missing information?
Sorry, I didn't. Where?
How you deal with missing information?
So there's this notion that exists of imputation, right? And there's various ways to impute data. Now you can impute data. So for example, if you don't know somebody's gender, right? But however you know their first name, there's a good guess that you can make what the gender is going to be. In some cases you won't be able to. In most of the cases you'll be able to make what the guess for the gender, right? So you can build classifiers, and this happens before we even get to the last step. You can build classifiers that can actually predict different types of attributes based on the other attributes that you have. Yeah?
Are you using the default analysis or did you write your own?
We ended up writing our own. The default analysis was a good starting point, but I think they were more geared towards traditional text search than what we wanted them to be, right? So we ended up tweaking and customizing a lot of our, and then we also wrote custom algorithms that went in as extensions to the framework.
One question, so how do you decide like what boosting to use? You mentioned you can tweak the matching.
The magic of machine learning, right?
Okay.
So the problem is as follows. You have different scores, and you want to combine them together, right? And that's in my case, the combination is I'm just going to sum them up together. What I don't know now is whether I should pay more attention to first name and last name or whatever, right? So in machine learning, we do this all the time, right? Where we have a different type of data points, and we were trying to figure out what's the best possible combination of this data point, right? And this is the process of machine learning, algorithms learning the weights of what the combination looks like. And I give you the example of logistic regression that does this all the time, right? Linear regression does the same thing. If I give you maybe 2 data points, you can figure out what the line is based on slope and y-intercept, things like that. And then you can tell me that this is the proper weight for this line. So fitting your data to a certain models, we do an activity that we do all the time using computers, using machines, and it's easy to do. So I would say don't try to guess it. Maybe you want to guess it. Maybe there's some heuristics that should be applied. Right? What I would have done is I would have used those heuristics or those expert knowledge as maybe features back into my learning algorithm. Quick question. Anybody else?
All this would be run like when you are in the query, querying the data, like for example, if you like all the machine learning part of it.
So the machine learning part of it happens once, right? It happens once, tells me for when I take an entity from here and query it against that one, these are the weights I should use for my different match strategies. Okay? That doesn't happen all the time. What happens all the time is I pick this guy and I run against there. Then I pick this guy and I run it against all of them there. That happens programmatically where I'm just doing bipartite.
There's no changes in the attributes and you don't go back for the
No, you don't have to, right? Because you've already learned from this data what the weights are going to be. You don't have to go, unless your data changes again. Unless you get a whole injection of new data, and then maybe you need to relearn the weights at that particular point. But if the data hasn't changed, there's no point in learning the weight for every query. It doesn't make sense. Thank you very much. Yeah?
What's your favorite database?
What's my favorite database? So I really like Titan. And I think the Cassandra people ended up abducting it and taking it away. So Janus Graph is now, I guess, the rebirth of Titan. So I like that. I stay away from the DB, is it DB4 or what's the graph database that, anyhow. I went the Titan way because it was flexible and it scaled really, really well. And I could put on top of my HBase or my Cassandra implementation, right? So it gave me a lot of options. And then it was easy to work with. My background was working with RDF graphs, which I didn't like a lot because they use a different type of structure to present information. You get to the same point, but in a much more painful way. Right? So Titan was a really nice, refreshing and surprise. Like, okay, so you can actually work with this at scale, which it works, right?
What's your favorite blockchain?
I don't have a favorite blockchain, and I don't have a Bitcoin wallet either. So don't ask. All right, thank you very much.
Yes,